So now we'll start with the fundamental theorem of the linear equations. So here we'll do a brief review of this theorem because this theorem we would going to use it later for deriving the results related to the controllability and also of the observability. In this controllability week, we would also use some of the tools we had discussed in the last week related to the quadratic forms and the norms as well. Okay, so for given a m cross n matrix W, we define two. First of all, we will define two subspaces. One is called the range subspace, and the second is called the null subspace. So the range or image is the set of vectors y for which y is equal to wx has a solution x in an n-dimensional space. That is to say, the image. So we would represent whenever we are talking about the image of any matrix by this symbol. Image of W is defined as the set containing all the y's in the m-dimensional space such that there exists x into the n-dimensional space following this linear equation y is equal to wx. Now the image of W is a linear subspace of Rm, so this is straightforwardly clear, and its dimension is called the rank of the matrix W. Okay. So another point here to remember is that you can also write the rank of the matrix W is equal to the number of linearly independent columns of the matrix W, which is also equal to the number of linearly independent rows of W. Say for example, because we already know that the matrix is of m cross n, so the rank of the matrix W is basically, first of all, the minimum of either m or n. Okay, or maybe it could be lesser than the m and n if the matrix is not full rank. Another space is called the null space, or the kernel is the set. We use this symbol kernel of this matrix W. Kernel of W contains all those vector x which satisfies this equation, that is multiplying that vector with the given matrix W, it yields a zero vector. Okay, so the kernel of W is also a linear subspace of an n-dimensional space, and its dimension is called the nullity of the matrix W. So if we are talking about the dimension of the image of the matrix, it is called the rank, and the dimension of the kernel of the matrix is called the nullity. So after introducing these two subspaces, we are now in a state to state the fundamental theorem of linear equations, which is given by here, that for every m cross n matrix W, the dimension of the kernel of the matrix W plus the dimension of the image of the matrix W is equal to the number of columns of this matrix W. Right? So dimension of the kernel of W we have defined as the nullity. So you can write this in this way also, and the dimension of the image we have defined it by the rank. So the nullity plus rank should be equal to the number of columns of the matrix W. So there also exists a simple relationship between the kernel and image subspaces, but before that we will introduce one definition of the orthogonal complement of a linear subspace V, which is defined by a perpendicular sign on the subscript of the space V. So it contains all vectors that are orthogonal to every vector in V. That is, so if we have this, we define this V perpendicular is equal to all those x such that the multiplication of all those z belonging to the subspace V multiplied with the transpose of the vector x yields 0. Okay, so this would be a scalar quantity, right? So we have the next result, which says the range versus null space. For every m cross n matrix W, the image of the matrix W can also be represented as the orthogonal complement of the kernel of the transpose of that matrix, and vice versa, that kernel of W is equal to the orthogonal complement of the image of the transpose of that matrix. Okay, so these two results are pretty much standard results, which you can see in the book of Strang, Linear Algebra and its application. We won't be carrying the proofs of these two fundamental theorems, but we will be using this to derive the results regarding to the controllability and observability. Next, we see the reachability and controllability gramians. So as the name suggests, the gramians allow one to compute the aforesaid subspaces. So now we are pretty much clear about that what are the different two subspaces for studying the controllability and reachability. Now we want to compute those subspaces. So to compute directly those subspaces, we will introduce these gramians. In fact, in the example what we had considered previously, we saw a bit of glimpse of computing that subspace, particularly for the parallel interconnection of the systems. But now we will uniformly define that how you can use the gramians to actually compute those subspaces. So given two times t1, which is greater than t0 or greater than equal to 0, the reachability and controllability gramians of the system of the pair AB of continuous linear time varying system are defined by, so we use this symbol WR reachability gramian and WC controllability gramian. So WR T0 comma T1 is defined by this integral T0 to T1 phi, which is the state transition matrix. B is the input distribution matrix and their transposes. Okay, similarly WC is state transition matrix with T0. So we already had seen the slight difference between the reachability and controllability subspaces when we had specifically seen that there's merely a change of T1 and T0 by computing the reachability and controllability subspaces. So there are two properties associated with it, that both gramians are symmetric and positive semi-definite. So note this point, positive semi-definite at this moment, because we will define one key result later on with respect to linear time varying systems. Okay, so this WR and WC would be the square matrix or dimension n cross n. Now it is straightforward to see that if I denote this complete thing by a matrix gamma, big gamma, so this part is nothing but gamma transpose, the transpose of the gamma. So similarly goes for the controllability gramian. Now if I take the transpose of this matrix WR, it again I would going to have the integral of gamma into gamma transpose. So this matrix is symmetric. Now since this would, if we talk about if gamma being the scalar, then basically it would be the square. So it can never go to, or it would definitely be a non-negative number or a matrix. So that's why we have defined positive semi-definite. Okay, because either it would be positive or 0. Now before stating the results, let's recall the three important terminology we have introduced so far. This is the reachability subspace given by the set x1, for which there exists a u such that x1 is given by this one. Okay, we have also defined the reachability gramian by this equation and the image of any matrix W by this set. So now we would going to set up some relationship between these three important terms or three important equations such that we could compute the subspace in terms of gramian. So the key result here is that given 2 times T1 greater than T0 greater than equal to 0, the reachability subspace from T0 to T1 is basically equal to the image of the reachability gramian matrix. Okay, this is the first result. Second is, moreover, if x1 is equal to WR into eta 1 for some eta 1 vector, which is equivalent to saying that x1 belongs to the image of WR. Okay, because if you see this definition, image of W, it's all those y such that y is equal to Wx. Now here y is x1, W is WR, and x is some eta. Okay, so we can say that if x1 belongs to the image of the matrix WR, the control or the specific control signal given by B transpose and phi transpose into eta 1 for all t belonging to T0 to T1 can be used to transfer the state from x from the origin to some finite value x1, some finite vector x1. Okay. So this is like I said, this is one of the key results. So we shall see the detailed proof of this important theorem. So the proofs would be done in two parts, because both these, first of all, you should see clearly that this one and this one are two subspaces. This is a reachable subspace, and this is also a subspace, image subspace of the matrix, or the for the matrix WR. So if we are able to show that for some x1 belonging to this space implies that x1 would also belongs to this space. Okay. The second part is x1 belonging to this space implies that x1 would also belong to this space. So basically we want to close the loop. Once we close the loop, it becomes an equivalent sign. Okay, it becomes an if and only if condition, what we had seen so far, right? So let's see the proof of the first part, that x1 belonging to this space implies that x1 also belongs to this space. So we recall two equations. One is the reachability Gramian. This is the equation what we had seen, and this u of t which we want to prove. Okay, for some specific input. So when x1 belongs to this space, that is image of WR matrix, we could say that there exists a vector eta 1 in the n-dimensional space such that x1 is equal to WR into eta 1. Right? This is what the definition of the image of any matrix. Now to prove that x1 also belongs to the reachable space, it suffices to show that the input ut, which is given here or which is given in the theorem, does indeed transfer the state from the origin to some x1 at t1. Okay. So to verify this, we use the variation of constants formula for the input, which is given by this one, x of t1 given by the integral t0 to t1 state transition matrix B into u. Now if I put this u here, which is given in the theorem, I would get phi into B transpose and phi transpose in eta 1. Okay, now this is the u which I have taken from the above. Now see clearly that this whole part is nothing but your WR, the reachability Gramian. So I could write is equal to WR into eta 1, and WR eta 1 is nothing but x1. Right? So this is the overall proof, the first part, that x1 belonging to the image of WR implies that x1 would also belongs to the range subspace for this specific u. Okay, meaning to say that there exists some u. Now going for the second part, x1 belonging to this space implies x1 would also belongs to this space. To see the proof, so what we want to show, that when x1, this which is given condition that x1 belongs to the reachable space, we know that there exists some input u for which this equation is satisfied, right? Now we show next that this also leads to x1 belonging to this image of WR, and using the one of the previous results, I could replace this WR or this image of WR by the orthogonal component of the kernel of the transpose of that matrix. Now since WR is symmetric already, I have directly written WR. Otherwise it should be the transpose of the WR. Okay, which is to say, so if x1 belongs to here, meaning to say that for all etas belonging to the kernel of the WR, it should satisfy x1 transpose eta 1 is equal to 0. We have directly borrowed this from the given definition and the fundamental results of the relationship between the kernel and the image. Okay, so now now given this, we need to prove this, and proving this is equivalent to showing that there exists, or this equation is being satisfied for all etas belonging to the kernel of WR. Okay, so let's see. So to verify that, we'll pick some arbitrary vector eta 1 which belong to this space and compute directly the left hand side. And the left hand side is given by this x1. If I take the transpose of this x1, I would get u transpose, b transpose, and then phi transpose, u transpose, b transpose, phi transpose, and multiplied by eta 1, because eta 1 is some constant vector. So I can take this inside the integral. Okay, now we will compute further the quadratic form of this form, where eta 1 transpose WR into eta 1. Okay, now here I have directly written WR as it is. So we would have eta 1 again is a constant vector. I can take eta 1 transpose and eta 1 both inside the integral, and this part is basically WR. Okay, phi into B transpose and phi transpose. Now note here that this complete part, is the transpose of this one, meaning to say I could write it as a square of the norm of this entry, B transpose phi transpose eta 1, the square of that norm. Okay, so this is, I have directly used the property of the norm. Now, but we know already that eta 1 belongs to this kernel of WR. So, which implies that WR into eta 1 should be equal to 0. Right? So, here we have this WR eta 1. So, this part would definitely be equal to 0. Right? So, we have some integral norm square is equal to 0. And this implies, and by, or let's say by using the property of the norm, this could be 0 only if the matrix in or the vector inside the norm itself is 0. Right? Otherwise it cannot be 0 for all tau belonging to T0 to T1. Okay? Now from this equation and the third equation, we conclude that 2 will definitely hold, because we started from the left hand side. We have proved that the right hand side is nothing but equal to 0, which implies that x1 belonging to the reachable space would also means that x1 would also belongs to the image of the matrix WR. Okay, so this completes the overall proof of the reachability Gramian. Now similarly, we could use the controllability Gramian to compute the controllable subspace. Given 2 times T1 greater than T0 greater than equal to 0, so the controllable subspace is given by the image of this controllability Gramian. Moreover, if x0 is given by this one, which is equivalent to saying that x0 belonging to the image of the matrix WC, the control, this specific control, can be used to transfer the state from some non-zero initial condition to 0. Okay, so the proof of this part would almost remain the same of the part we have seen for the reachability Gramian. Okay, so we won't discuss in detail the proof, but this result is also important, because once you have computed the Gramians, you could directly compute the subspaces. Okay.